Nuclear bombs, mythical, terrifying, and world-changing. But what are they really? They're not just bigger versions of regular bombs. Their power comes from the tiniest building blocks of matter atoms. At the heart of every atom is a nucleus, packed with protons and neutrons, held together by a powerful force. Most nuclei are stable, but some, like certain uranium atoms, are unstable, ready to unleash massive energy. If you split one of these unstable nuclei, you get a huge burst of energy. This is nuclear fission. Imagine a tightly coiled spring suddenly released. That's the energy from fission. This process powers both nuclear bombs and nuclear power plants. The same science that can destroy cities can also power them, treat diseases, and help us explore space. It's a double-edged sword. The energy source is the same, but how we use it changes everything. So, how does this all work? Let's break it down. Everything, us, the air, the screen you're watching, is made of atoms. The nucleus is where the action happens, and for some atoms, it's a ticking energy bomb. When we split that nucleus, we unlock the energy that powers the atomic age. This is the science behind the most powerful technology humans have ever created. Let's dive into the details and see how it all comes together. Ready? Science is about to get explosive. Let's go! There are two main ways to get energy from an atom's nucleus: fission and fusion. Fission splits big atoms like uranium or plutonium, releasing energy and more neutrons. These neutrons hit other atoms, causing a chain reaction, controlled in power plants, uncontrolled in bombs. In a nuclear power plant, the chain reaction is slow and steady, boiling water to spin turbines and generate electricity. In a bomb, the reaction happens almost instantly, unleashing a massive explosion. To make a bomb, you need a critical mass, enough fissile material for a runaway chain reaction. If you don't reach critical mass, nothing happens. But if you do, the energy release is exponential. Fusion, on the other hand, smashes light atoms together, like hydrogen, to make helium, releasing even more energy. Fusion powers the sun and hydrogen bombs, which use a fission bomb as a trigger. So, fission splits atoms, fusion fuses them, and both can be harnessed for power or destruction. The difference is in the control, and the scale of the energy released. That's the science behind the bomb and the power plant. It's all about how you start and stop the chain reaction. Next, let's see why these bombs don't just explode by accident. Why don't nuclear bombs explode if you drop them? Because they're engineered not to. The fissile material inside is kept in separate, subcritical pieces, safe on their own. In a gun-type bomb, two uranium pieces are slammed together by conventional explosives to form a critical mass. In an implosion-type bomb, high explosives compress a plutonium core to make it supercritical. Both designs require perfect timing and precise engineering. If the process isn't exact, the bomb just fizzles. Multiple safety systems prevent accidental detonation, even in a crash or fire. The bomb's parts are kept separate or in a safe mode until a specific arming sequence is completed. It's not a simple trigger. It's a complex machine that only works when everything happens in the right order. That's why you can't just drop a nuclear bomb and expect it to go off. It takes deliberate action to unleash its power. The engineering is as impressive as it is terrifying. The atomic bomb's story began in quiet labs, not battlefields. In 1938, Otto Hahn, Lise Meitner, and Fritz Strassmann discovered nuclear fission by accident while bombarding uranium with neutrons. Meitner and her nephew Otto Frisch realized the uranium nucleus had split in two, releasing energy. Einstein's equation, EMC2, explained it. A tiny bit of mass lost in the split became a huge burst of energy. The news spread fast. Scientists saw the potential for both power and destruction. The timing was critical. World War II was looming, and the fear was that Nazi Germany might build a bomb first. This fear set off a global race to harness the atom. The discovery of fission was a turning point in science and history. It showed that splitting the atom could change the world. Forever. The scientists' curiosity unlocked a force that would shape the future. Their work led directly to the most secretive and ambitious project of the war. The atomic age was about to begin. The stakes couldn't have been higher. Next, the race to build the bomb. Fearing Nazi Germany's bomb, scientists urged the US to act. Einstein's letter to President Roosevelt sparked the Manhattan Project, a secret race to build the bomb. Led by General Leslie Groves and physicist J. Robert Oppenheimer, the project brought together top minds in secret cities. Oak Ridge enriched uranium. Hanford produced plutonium. Los Alamos designed the bomb. The scale was unprecedented. Factories, labs, and entire towns built in secrecy. Scientists worked under immense pressure, racing the clock and wrestling with moral questions. On July 16, 1945, the first atomic bomb was tested at Trinity Site in New Mexico. The explosion was unlike anything seen before, a blinding flash, a towering mushroom cloud. Oppenheimer quoted, "Now I am become death, the destroyer of worlds." The atomic age had arrived. Less than a month later, bombs were dropped on Hiroshima and Nagasaki. The war ended, but the world was forever changed. The power of the atom was now real and unleashed. The race was over, but the consequences were just beginning. What would we do with this new power? After the war, scientists asked, could atomic energy serve peace, not just war? The answer, yes. The Atoms for Peace movement aimed to harness nuclear power for electricity. Nuclear plants use fission to heat water, create steam, and spin turbines, just like fossil fuel plants, but without burning anything. The result, huge amounts of clean energy from tiny amounts of fuel. Nuclear power produces almost no greenhouse gases, making it vital in the fight against climate change. A single uranium pellet can generate as much energy as a ton of coal. Nuclear plants provide reliable, round-the-clock electricity, baseload power. But challenges remain: safety and nuclear waste. Accidents like Chernobyl and Fukushima raised fears, but modern reactors have advanced safety systems. Waste disposal is still a technical and political challenge, but solutions are in development. Nuclear energy is a powerful tool for a low-carbon future. The atom's promise goes far beyond the bomb. Nuclear technology isn't just about power or weapons, it's saving lives and improving the world. In medicine, radioisotopes help diagnose and treat diseases like cancer through imaging and radiotherapy. Radiation sterilizes medical equipment, ensuring safety in hospitals. In agriculture, radiation creates hardier crops and controls pests without chemicals. The sterile insect technique uses radiation to reduce pest populations safely. In space, nuclear batteries power probes like Voyager, far from the sun. On Earth, radioisotopes help trace underground water, aiding in resource management. The atom's reach is vast, from hospitals to farms to the stars. Nuclear science is a versatile tool for progress. Its benefits touch nearly every aspect of modern life. The peaceful uses of the atom are as remarkable as its destructive power. Harnessing it wisely is key. Nuclear technology is a double-edged sword, capable of immense good or catastrophic harm. The same science powers cities and threatens them. The risk of nuclear weapons is the greatest threat we face. Proliferation increases the danger. Even a small nuclear conflict could have global consequences: nuclear winter, famine, collapse. Yet, peaceful nuclear tech fights cancer, improves crops, and provides clean energy. In a warming world, nuclear power is a crucial tool for cutting carbon emissions. The debate: how do we maximize benefits while minimizing risks? It takes international cooperation, strict safety, and non-proliferation. We can't unlearn the science, but we can manage it responsibly. The choice is ours: use the atom to destroy or to build. The future depends on how we wield this power. The conversation is ongoing and vital. The story of the atom is one of power and responsibility. Splitting the nucleus can lead to destruction or progress. Our challenge: encourage peaceful uses, guard against military ones. Treaties like the Non-Proliferation Treaty and agencies like the IAEA help keep the balance. New reactor designs promise safer, cleaner, and more efficient nuclear energy. Some can even use nuclear waste as fuel, solving storage problems. The journey that began with early scientists continues today. The atom's story is a human story: curiosity, creativity, and wisdom. We can use this power to threaten or to heal. Understanding the science and the stakes is the first step. By staying informed, we help ensure a safer, brighter future. The choice is ours. Let's use the atom wisely.